Yeah, super fine. Admit, yes. Okay, so I think a lot of people are there, 17. I'm glad that so many people are there. And yeah, so I'm having some technical problem with this camera on, turn on the camera, which I'm not able to do. Anyway, I will just start with a brief introduction, but still people are joining. Yeah, admit, admit. Hmm. Few more minutes. And yeah. So when I'm presenting, I may not able to see anyone or anything. So it's better someone just responds. Okay, if something is not, if some, let's say I'm not be audible or my slides are not visible, you may not see the uh, some other technical glitches may be there, but you just stay there and inform me. That's it. Super cool. Yes. So I think you all of you have already seen the classes, I mean the lectures taken by ma'am, at least the week one. And from that part, I mean anything relevant to that part will be discussed here. And just one more minute, okay? I will start. Admit. Okay, let's come back to our discussion. Before I go there, let me check I'm recording or not. Yes, I'm recording. So, hello, hi everyone. My name is Manajit Das, and I'm a TA of this course, Organic Mechanisms in Organic Chemistry, right? So, welcome everyone. So, what is the goal? Which I have already told in my first YouTube video. I mean, you can see it there. Come on. Then I have to admit people also. Sorry. Yes. I hope there will be no one to join right now. Okay. So, uh, the point is, I will discuss some questions and then some simple answers of those questions in this session, and this will be directly from the week one part. Okay. And my topic is like introduction to nucleophilic addition to carbonyl system C112. If you have any doubt, just let me know. I will try to solve those. And for this class I'm using this book, a guidebook to mechanism in organic chemistry. Some of you mailed in the, oh my god. So I think some a lot of people are joining still. I may not able to take anyone more. Let's see. I'm just continue with this. So here, as I said, a guidebook to mechanisms in organic chemistry. This will be focused. This book I have referenced here, and then this book is written by Peter Sykes. Now I will relate this topic to ma'am's class. Like if you follow the lecture 2 and 3 and lecture 4 also, so ma'am has introduced this concept like electron sources and electron sinks, right? So, okay, just a second. View all, admit all. Please let me know if things are visible or not. Am I audible or not? Okay. So these things are all, I mean, pretty clear from the classes that what are the electron sources and then what are the electron sinks. These are very crucial information, and these will be uh, taught in every other reaction mechanisms. Okay, I mean, in terms of nucleophile or electrophile, they may not use this electron source and sinks, but this is very easy to follow, and it's interesting too also. So, for example, electron source, we have been introduced to this like neutral molecule. For example, this ether, ROR, which this lone pairs act as the electron source, and it is the non-bonding electrons. Similarly, this RSR, this can also sulfur with its lone pair can act as an electron source. This molecule NR3. Similarly, PR3, these all are acting as electron source. Similarly, this oxygen atom. Overall, any atom with its non-bonding electron pair can act as an electron source. That this is electron rich, so they will like so, okay, so this they are electron rich, right? So what uh, they will like is a nucleus. So these are the thing, and then there can be charged species also. For example, Ro negative charge is shown here, and then this carboxylate anion is also there, cyanide, azide, and halide is also there. All these act as an electron source. Now, similarly, electron-rich bonds, for example, RMgx. So here R, I mean, if you see the polarization here, R is delta minus and then Mg delta plus. So this R with its electron pair, it acts as a electron source. I don't know how much. Okay. Hmm. So these are act as the electron-rich bonds. For example, RLi, R2CuLi, R2Zn. And then hydride reagents, lithium aluminum hydride, sodium borohydride, sodium hydride, and BH3. So overall, these act as an electron source. Now, in my other slides, you will see that how these are used in this carbonyl addition. Okay, and then similarly, there are other electron sources can be possible, like these pi bonds here, this simple alkene, this conjugated diene, and then alkyne, this allene, benzene, all are possessing pi bonds, which are easily can be donated to one vacant space or vacant orbital. So electron-rich pi bonds, for example, this here O minus can also act as a source electron source as well as this pi electron also. Similarly, OH can with its lone pair and also this pi electron, and then N with its lone pair and then pi electron also source. And then these are termed as electron-rich pi bonds because this oxygens with the negative charge can donate come here with the resonance, which you are already familiar with, I hope. Then we'll be talk about electron sinks. So there are, for example, empty orbitals like carbocations. Here, there is a p orbital which is empty, and this Lewis acid, aluminum trichloride, FeBr3, and then acidic hydrogen H plus, this carboxylic acid H, and water, and then alcohol. All these can act as electron sinks. Now, why did I introduce all this at the very beginning? Because these in every reaction I will discuss will involve this particular terms, electron source and sinks, and we'll try to identify what are the electron source and what are the electron sinks, and from there we'll draw the arrow pushing mechanism. Basically, that's the funda. Now, before I go into my other slides, let me discuss some basic fundamental point of carbonyl chemistry. So I have my this book which I'm going to read. For example, say it's very simple sentence. Okay, carbonyl compounds exhibit dipole moments. You know from that, and because the oxygen atom of the CO group is more electronegative than the carbon. So in the if I just a second, let me admit. Please let me know if anything is not clear to you. Okay. And I will follow from here. So we all know this carbonyl group here. It's a simple let's say this methyl. This is Me, and this is also Me. Now we need to find this electron source or and then sink. So oxygen with its lone pair, for example here, I have shown two lone pair. Okay, and also because of the, so this can act as an electron source, right? It can give to any other system. Furthermore, since the electronegativity difference between this carbon and oxygen, so there's a dipole moment will be there, and this there will be inductive effect also. So for example, this the oxygen is more electronegative from the Pauling scale, you know, which is ma'am has already shown to you. This becomes delta positive and this becomes delta negative. Hmm? So any species, let's say I have X. X is an electron source, so it will like basically it will like nucleophile. So nucleophilic addition. So it's a nucleophilic addition. So my point of discussion is that it can add. So I'm showing arrow pushing mechanism, which is very simple. No need to write this draw. I mean arrow within so much jiggly way. So this X minus can act. I mean this attack this delta positive center, and then this pi bond can break and it come to here O minus. So this is a very simple thing, right? So let's clear the frame. Now with this simple concept, we have shown the electron source and sink within the same molecule, right? So depending upon the reaction condition, it can act electron source and sink at whatever point. So let me go to the next slide. Oh, there are some other things also. I forgot. So there are, for example, methyl halide is shown here. So carbon in polarized sigma bonds. Basically the charge separation here, X delta minus and C delta plus, which is shown for the carbonyl system, and it is shown in the below portion also. C delta plus and then oxygen delta minus. So nucleophile will come here and attack. So these are pretty simple scenarios you can think of. Now here comes this questions and answer of some of the question from this book Peter Sykes, which you can follow. And first is simple addition reaction. Now I forgot to mention one more thing is like that in the classes ma'am has already told about different types of polar reaction mechanism and then radical mechanism. So there was like substitution, elimination, addition, and then addition elimination and then elimination addition. So overall those things are discussed, and at the same time there was reaction mechanisms also shown. Within that part I will just go some other reaction example within this same scenario. So simple addition reaction, so we will start with hydration reaction. So hydration, and our focus was like carbonyl system, right? So we will have a carbonyl system and hydration. Immediately we can say that there will be then water. That's why hydration, simple. So if I draw the simple reaction path, or not path, the schema, reaction schema, it looks like this. I will describe it. So in the left side of this equation, you see there is an general carbonyl system, like it can be aldehyde and ketone depending upon the substituent R1 and R2. And then we have water which will be reacting. So that's why it's hydration. Who is getting hydrated? This carbonyl system is getting hydrated. Again, someone is trying to admit. Okay. Anyway, so let's come back to our point. So we are interested in hydration of this reaction. Now the question is what is the mechanism, right? So mechanisms of organic chemistry. Now what is the difference from left to right? You see that this OH, for example, this carbonyl carbon is converted into this OH, and then one from H2O, there is, we can see there is one OH group is also here. Overall, from a trigonal planar structure, it's formed a tetrahedral structure, right? Now there are a couple of points to mention here, which I will just read. Now imagine you have acetaldehyde and formaldehyde. There are two systems. So, and if someone asks you whether it will form hydrate or not, now what happens is that many carbonyl compounds undergo reversible hydration in aqueous solution, which I have shown here. And you see the arrow. So reversible hydration, simple. So it's an equilibrium. So there will be equilibrium constant, right? And the equilibrium constant for formaldehyde, acetaldehyde, and others varies. For example, formaldehyde it's like up to 10 to the power 3, and then acetaldehyde and it is lower like 1.4. So it may not be clear to you. For example, let me draw such things. So what I'm saying, this hydration mechanism, mm, will compare this H, and then we'll compare with this one, methyl, and then hydrogen. So here is a methyl. So we are treating both with water. This is the simple question. So both will treat with water. I mean, it's just taken in water. Simple. So question is the equilibrium value, K equilibrium for the hydrated. This one product will be like this. So there will be OH here, and there will be OH here, and there is H, and there is H. So this one. So let's say we put it name as K1, and then similarly we'll have the product here, and there is a methyl, and then there is a hydrogen, OH, and there is OH. So there are K1 and then K2. So what we say that the observation is that K1 is larger than K2. So this is the observation. The equilibrium constant for this hydration for the formaldehyde is larger than MECHO, right? So this is we know. I mean, for example, how this happening. That is, we'll come to that point later. But we want to discuss how this is happening and why the rates are different. So rates are different because of this methyl group here at the right side. Methyl group is electron donating group. So inductive effect, resonance effect, and then whatever all are discussed, right? So methyl group is electron donating group. Thus, it reduces the delta plus character at this center. Whereas this hydrogen is not having such any effect. So their delta positive charge is here more. So it is this carbon center is much more electrophilic. So it will have more tendency to attack by this oxygen lone pair. Okay, so this is the nucleophile and this is the electrophile, because it is loving electron and it is loving nucleus. So that's why the reaction, what will happen, this oxygen of the water molecule will react faster here, and it will push the pi electron to the oxygen atom. So this point, and I will show it again. So I will show the mechanism here. So we have hydrogen and then hydrogen. I'm showing just a single arrow anyway. And then we have water with its two lone pair. Sorry. So it attacks here and then it moves there. What we get here is basically a tetrahedral species. So O, and then hydrogens are there. And then there is a hydrogen, and O negative. Simple. And then this is a positive charge here, so there will be proton transfer kind of thing, and this will be OH, and there will be another OH, and this is a hydrogen. So this is the simple thing. This is the product. I hope this mechanism part of this simple hydration is clear to you. Okay, and then similarly we can follow the others also, right? Now, one second. So now we got the mechanism how the hydration of this carbon system happens. Now the question is why the rates for the other aldehyde and ketones are very slow. So it is actually the equilibrium most of the time tends toward the left side, not toward the right side. But there are some systems which are be like interesting to show. One example is like this one. Here, if you follow the reaction schema, this substance like CCl3CHO in presence of water, it forms this hydrated species, right? Okay, so what happens here again? What happens here? You know that water will attack here, and then this will form OH, and this has a very high K equilibrium. So overall, it mainly happen in the right side. For example, if I read So what we understand from the mechanism part, that electron donating substituents inhibit hydrate formation, right? For example, formaldehyde, it was much faster and then compared to the acetaldehyde and other acetone. Hmm? So electron donating substituent inhibit hydrate formation, pretty simple. Whereas opposite way, electron withdrawing ones promote it. So here CCl3CHO. So this 3 chlorine containing CCl3 group electronegativity, you know. So it is an electron withdrawing effect, so it will have electron withdrawing effect, thus the carbon center becomes more susceptible to this nucleophilic addition. Okay, so electron withdrawing ones promote it, thus K for the hydration of CH3CCHO is 10 to the power unit of 10 to the power 4. And this aldehyde, so its name is trichloroethanol. Powerfully electron withdrawing chlorine atoms destabilizes the original carbonyl compound. So let me describe it, how it destabilizes the original carbonyl compound. So I will try to draw the mechanism again. So let's clear the frame. So what we have is this carbonyl, it's an aldehyde, simple, and then C and then Cl3, right? So you know how to draw the corresponding resonating structure of this system. For example, I can draw here O and then negative and then plus here, and there will be hydrogen. So Cl, so this Cl and this Cl. So what happened is that because of this chlorine's electron withdrawing power, so overall it destabilizes the carbonyl system. Here the positive charge is there and it is still, this CCl2 group is electron withdrawing. So overall it destabilizes the original carbonyl system, but not the hydrate, whose formation is thus promoted. But what will happen when it is forming an hydrate? So just a second. So if I remove this and I'll just make it hydrate, okay? I hope you will get it. So there is a OH here, now there is a OH here. Now what happened, this overall this push, so this one favors this formation. How? Because of the hydrogen bonding. So if I draw it properly, so for example I am drawing this hydrogen here, and you can see this chlorine is electronegative, so it can form an interaction. Okay, so thus this hydration, I mean the K equilibrium is very high. So I will show similar form at the here also. Let me change the color. It will be easy. So there is a OH group, right? So this chlorine can interact with this hydrogen. So this hydration formation is facilitated. I mean it's very fast. Someone is trying to get at me. Okay. So that's why we see that the K equilibrium constant for this reaction is up to the order of 10 to the power 4. So the equilibrium mostly tried toward the right side. So because this electron withdrawing effect of this CCl3 group makes the hydrate formation very easy. Similarly, I will have a second question in this slide, which you have to answer. And there I go. So what is the product of this reaction? I will give you some 2 minutes to think, and if someone can try to answer, I would be very happy. I will show it. Okay. So I will give you 2 minutes. Okay, just think about it. Our this will form hydrate. I mean, this will undergo hydration. Okay, hydration reaction. Simple water addition, nucleophilic addition to CO. You can draw it in your paper and think which carbonyl group will undergo hydration and what will be the structure of the product, and the mechanism is very similar to what I have shown already. I hope the question is already clear to you. And let me go to this side. Okay, so I can see a lot of people are there. If anyone is interested, just show it, or you can raise hand, let us know. Please feel free. Middle carbonyl group tetrana, very good, nice. Anyone else? Okay. If not anyone else, then I will just show the structure, right? And I will just go with the simple. Here I go. Let's clear the frame and make it big. So what we have is this carbonyl group, and then there is pH. I'm not drawing fully, just pH, and there is a carbonyl group and this carbonyl group. So overall, this carbonyl group with its electron withdrawing power destabilizes this carbon plus center here, plus delta minus. Okay, and then from the product side, if we see here, of course, the equilibrium will. Just a second. Admit. Yes, move it. So this water molecule, as usual, with its lone pair, which is like our electron source, and there is electron sink, and similarly it will go there and it will form OH. It is very simple from this side. Now the plus point from the product side is that it can form hydrogen bonding, which is nice to see. Mm, Someone else is also trying to join. Okay. Now what will be the products? Let's us draw. So I will just try to draw it tentatively. I mean, it's not so accurate. Anyway, so basically, what I need is that hydrogen is there, and one O from this side and OH. So there will be carbonyl group, and also there will be carbonyl group. This has a hydrogen bonding like this. This is a hydrogen bonding like this, and also we have pH. See, so overall this hydrogen bonding and the destabilization from the reactant side is favors this K to shift to the right side. See, so let me number it so it can be easy to follow you. So let's say this was 1, this is 2, this is 3. You follow the 2, it just 2 OH with the same carbon group, right? This OH and this OH, and this was 1 and this was 3, right? This is very simple. This is an interesting example from this hydration mechanism. I hope it is clear to you. Now I will let me go to this, and if you have any doubt with these things from this hydration mechanism, any problem, any question, you can message it also if you have any problem with it. Okay, Nasim also answered middle carbon. Thank you, Nasim. You were right. And yeah, good evening. So let's go to the some. So I wanted to discuss some other points also. Let me clear the frame. And so this mechanism which I already shown to you, and this hydration is generally not so much favored in neutral medium. So you need some acid catalysis, like acid catalysis or base catalysis. I will show little elaborate mechanism. I mean, with some few more steps, how the acid promotes this hydration mechanism. Basically, we are still dealing with hydration, but here we will talk about acid catalyzed and then base catalyzed system. Though this concept like catalyze and other things are not discussed, but it's very easy to follow, I think. So I am going to show a carbonyl system. So simple, acetone, and then we have an acid. Acid means and HA. So this is let's say A is the other part. So this is an acid, and then we have water, right? We are talking about hydration. So this is water. Now I'm saying this three part. Let me change the color. So here one, this is two carbonyl system. This is the acid. So acid catalyzed hydration mechanism we will talk about. What is the plus point here? As I said, it will drive the reaction towards the right side. So hydration will be fast. So there are so many things are there actually. So this there are lone pairs with oxygen here. I'm not showing. So it can attack this carbonyl center. First step. This pi bond will come here, and oxygen with its lone pair as usual. It will abstract this hydrogen. It's an acid, and then A minus will remove. So I have to admit also someone. Okay. So here you say this. What happened is that oxygen of the water molecule is attacking at the carbonyl center, right? And then this carbonyl oxygen is attacking the acid and it is accepting this H, and then A minus is getting removed. So I will show in this arrow, meaning that A minus is getting out here. So what will be the right side? So basically this will have a transition state. So I'm not showing a transition state, but it will have a corresponding transition state of these three, including three, all of them. Okay. Now what happened? It's simple. I changed the color. It should have been the same anyway. So O is now is bonded with hydrogen. This one, and there is OH2 plus, and there will be plus sign. So this is what we get, right? You just follow the arrows. So these are our friends actually to deal with what is happening. These arrows are very friendly to us. So then this A minus can capture this hydrogen. I'm showing in a single step. Okay, it can be considered a single step, and this will come to this oxygen. So overall, we get the hydrated product. So OH as usual, and then there will be OH, right? Simple, and we get back our HA. You see, so HA is not, I mean, it just helps the reaction. So it's an act as a catalyst. So HA was just there, it goes into the system and then it leaves the system. So it's a catalyst. So that's how it promotes the hydration of carbon system in acid media. Similarly, you can also think of as a same reaction catalyzed by base. So what will happen in case of base system? Let me draw it very carefully. Okay, just a second. Adnik yes, I can see how many people are there. 31. Okay, very good. No problem, no messages. And so this was the case with acid catalyst. How acid acts as a catalyst for this hydration mechanism. Now let's consider how can a base can help this hydration mechanism. So all I need is a base. So base we know. Let me change the color. So let's say we have B with it lone square base. So what will happen now? We don't have acid, right? So I don't need this acid part. So acid is not anymore fun. Okay. So what will happen now? Since we have base, so base will can abstract this H, and then it can bonding pair will come to this oxygen atom and it can attack as usual to this carbon system. So this will also have corresponding transition state, base catalyst. Now anyway, I have to remove all these things because these are not anymore of relevance here. Forget about this. I will come here. Okay, sorry. So it will have corresponding transition state, and what will happen? It's pretty simple. We'll have O and then H from the water part, and then this carbon which will become tetrahedral, and then there will be O minus. See the difference. At the acid catalyst system, there was OH which was forming from the carbonyl system. Now it is forming O minus, and what else we have is BH plus, right? How it is coming? We just follow here. B with this lone pair is abstracting this hydrogen, right? So that's why it becomes BH plus. And in the next step, what will happen? This O minus will capture this hydrogen, and B will be get back. So B removes as it enters, it removes also get out from the system. Overall, we get the same products. So we show that there are two pathways in acid catalysis and base catalysis. These are known as general acid catalysis and general base catalysis. Anyway, my focus is that hydration mechanism. This hydration can be made faster. So using general acid catalysis and general base catalysis. So that's a lot about this hydration. How we can get to the product side, and then which kind of substituent or substrate can be favored for this hydration. So this was there, and there are pretty good examples are also noted in the book. And then let's go to the next point. What we have, let's see. We have addition of alcohol, and alcohol is just pretty much exactly same with the water, right? It was just HOH. Here we'll have ROH. But there are some interesting chemistry with alcohol, like acetal, hemiacetal formation, and their applications are also very useful. And that's why I thought to include those things here, addition of alcohol. Can we draw the mechanism of it? Yes, we can. And then of course we will draw it. And this is an example. I just directly went to the question. Now I will give you some time to think about this question, let's say 2 minutes, and come up with any answer, or what do you think about this. uh, Anyone who have already done this, what is the review, how it will form, anything, just note the reaction please. Carbonyl R1 COR2 with an I mean it's an alcohol with a 2H group, and it is acid catalyzed. See, there is H plus and H2. Escape. Someone is trying to get in. Okay. Okay, fine. So anyone? I think the questions you have noted, right? Avinash, and then Vibhav, Jyotika, Krishi. I can see all of you. If you are interested, you can add. So we are just moving from hydration to alcohol addition. It's pretty same, pretty same. And then this is acid catalyzed. H plus and H2 is there. So that's why I showed you in the first how an acid helps to forming the hydration product. Can I see all of the participants? Yes, I can. Let's see. Okay. Yes, Avinash, Ajay, Anju, thank you very much for coming. And then double Nasim, double dehydration after addition of H2O. Well, great. Then anyone? Mm, so I will little change. I mean, Nasim pointed a very interesting point after addition of H2O. This gives me one problem which I have been having in the question. There is some problem with the question. So a little bit of, so this point, double dehydration after addition of H2O. Thank you, Nasim. Anyone wants to add anything else with this question? You can think of something. Okay, no one is interested to draw or say anything. Okay, fine. So let me go to my whiteboard. Right. So before I jump into that problem directly, I will have this again, our similar kind of mechanism. So yes, I wanted to add some point actually. So this reaction, it is this alcohol addition. So as Nasim said, water can also act as the say electrophile, right? Sorry, nucleophile. Water can act as the nucleophile. So it loves, it is having lone pair, so it will love nucleus. Now the question, the wrong part. I mean, it shouldn't be H2O. Sorry, huh? So it will be acid catalyzed, but not H2O. The H plus source will be something else. So H2O shouldn't be here. So there is some problem with this. So I will just remove the water part. Actually, water creates a lot of problem in these things. So I will come here, and there you go. No problem. Just have H plus. Anhydrous HCl you can think of. Okay. What I'm saying, anhydrous HCl. So there is no ambiguity. Now I'll show something. See, this is acid catalyzed, and if I follow mechanism properly, I should draw the mechanism like earlier I showed. Three component, all the arrows are going. Those should be the correct. But for the sake of simplicity, I will just draw very simple way. Okay. So let's say I have chosen the arrow. So this alcohol. So this is electron source, and this is electron sink. So just a second, Control Z, and then I can choose this electron. Okay. So OH can attack at this carbon, right? And this will come to this oxygen. Very simple. So what we will have, you will end up with, let's draw rather than saying. So this will Control Z. So this will come here, and then there will be oxygen here. Anyway, I will draw it later. And how many carbons are there? 1 2 3. Just stay with me, 1 2 1 2 3, and there will be oxygen. Sorry, Control Z. Just I will mention the name so it will be for easy to follow. Just a second. R1 as usual, and then we'll have, if anyone have any doubt, just you can message it. Okay, and then we have this oxygen, and this has converted to the OH part, and there was OH. I think this first step is clear to you. So this is the, just like water addition, there is an alcohol addition. Once again, I am saying this mechanism is very simple, not I mean thorough enough. So here happen, O, it's coming here, and then actually it was OH plus, and then proton transfer from to this O minus, and it becomes OH. Now what happens? This is, now it becomes interesting. So this is the first product. Okay, so this is known as, this part is known as hemiacetal. Hemiacetal. So remember this. If you imagine this second OH group from the diol is not there, it's in hemiacetal. What part is, I am considering hemiacetal, R1, R2. Then there is C, which is considered attached with one OH, and then ether kind of functionality. So this is called, this part is called hemiacetal. So let me draw it properly also. Control C, Control V. So this part actually, so whenever you see this, let's say this ether, so this is known as hemiacetal. Now the extra point is here that we have another OH group. So please stay there. Admit. Now what you see, there is another OH group here, and then we have acid. So what will happen basically, let me take the so this OH can attack this H plus. Forget about this downward arrow. And so what will happen, this will become OH2. So this will become OH2, and so this will become OH2. Let me write it so it will be very easy to follow. OH2, and there will be positive sign. Understand this? And thus it becomes a very good living group. Please follow the mechanism. And then what happens? So now there will Control Z. So this bond will get removed. So water will get removed. So once water get removed, it will form a carbocation. Please follow that. It will form a carbocation. Control C. So what it will form actually? So this is a little bit tricky. So here it will form a carbocation. So let me draw a positive sign here. That's it. So it forms a carbocation. Please, it should be planar, but it seems like I have drawn an NH3 kind of system. It's the planar system, right? So what I have, carbocation, and this carbocation you can draw the resonance structure. This oxygen with its lone pair can form an pi bond of system. So there will be corresponding resonating structure here. Someone is trying to. So what happens? We can form a carbocation, and this is stabilized by this oxygen atom with its lone pair. Please draw the resonance structure, right? Then what we have an extra, this OH functionality is there. We have a second alcohol group. So this second alcohol group, what it will do, it will attack this carbo system. So I hope this figure is clear to you. So this will come here. Remember, in between I have 3 carbon centers. So 1, 2, 3. It is correct. Okay. So don't worry about that. So overall, what it will become? So it will become OH plus, and then H plus will get removed. So, and let me remove this. What will happen is that it will form a bond with this system. Now let me, this figure is not good, so I'll just make it nice looking. Okay, just a second. So I can draw it, actually it's not a very good figure. Just a second. Let me try a little trick here. Yes, exactly, that's what I wanted to draw. Super good. Now this is the same structure, just I have drawn in a properly. Okay, so you see, this was our reaction and carbonyl system. and then this alcohol, diol with two OH group. Initially we form an hemiacetal with one OH group and then one ethyl group here, and overall at the end what we get, an acetal. Overall at the end what we get, an acetal. So this is what we call an acetal. So this reaction is very important, and this has some in application a lot of things, like for protecting some group. So you may be aware of some protecting functionality, how to protect some. For example, if I want to protect this carbonyl group from to not to react with any other system, so we can form an acetal. We will just treat it with this diol and it will form an acetal. And the plus point is that we can remove this acetal. We can remove this acetal, so we can get back. So what I'm saying, we can get back to this carbonyl system. Sorry. So we can get back to this carbonyl. So this is the acetal. Acetal can be brought back to this carbonyl system. Just treat it with water. So that's the problem with having water. If you have this acid is already there, H plus. If you have water, so it will get again break and it will come to the carbonyl system. So we can protect it and then deprotect it also. So this covers a lot about hemiacetal formation followed by acetal formation. So overall, if I summarize this, I have a carbonyl system and alcohol first attacks and it forms the hemiacetal. Then the hemiacetal undergoes this OH group gets protonated and forms the carbocation. Why carbocation? Because it's stabilized by this adjacent oxygen lone pair, followed by it gets another attack by this OH group and form the corresponding acetal. So this is the case of this reaction and this mechanism. So I have already changed this slide totally. So anyway, anyone have any question with this particular slide, this addition of this diol? Is it clear? Some message or like thumbs up, it will be enough for me. Anyone? Okay, yes sir, thank you so much, Nasim. And then let me go to the other question. So see, and all this point, like ma'am has told, like it's a build up from inductive effect, resonance, hyperconjugation, and then electron source, sink, arrow pushing. All comes to this place at the same time when you solve some question. So 99% of the time this will be based on such things. Okay, some exceptions will be there, as you know, chemistry is all about exception. Let's get back to the, okay, come to here. And now we'll see there are electron sources are of different type. We just talked about alcohol and water kind of system. Those were the electron source, and our electron sink was like from beginning to last will be carbonyl system. And we can have different electron source like hydride ions. This ma'am has shown already in your classes. So this is like very simple. This is a reduction of the carbonyl system to the alcohol. Lithium aluminum hydride we are using. Now if someone asks you what is the mechanism of this, you should be able to draw. So we'll just draw the mechanism. Okay, I'm not going to draw in ChemDraw. I'll just use the simple thing. Now generally what happens, people will just show you direct structure that what happens, let me show than speaking. So I have lithium plus, right? It is simple. And then aluminum hydride, so it's a tetrahedral species where aluminum is like, so this is the structure of lithium aluminum hydride. So there is a negative charge here. One simple way to people show is that this hydrogen with bond with aluminum with its, so this hydrogen with its bonding electron pair, again I am saying hydrogen with its bonding electron pair will attack this center, carbon center, which is electron deficient a little bit, delta plus and then delta minus, as usual every time we will draw this. So this will get back here and we expect the product. So what is the product? Someone is trying to do. Okay, just one suggestion from to everyone that please join at around 7:05 or 7:10, it will be fine. Okay, so what happened here is that, and then oxygen, let me other it will get missing. So this O minus, and so this is hydrogen, and then this lithium plus is already there. Now what happened is this aluminium would become AlH3. Sorry, AlH3, right? So I have what have AlH3, which is the Lewis acid, hmm? which is the Lewis acid. Now it will form the again the same thing, like O minus will come here. Hmm? So basically, what I will show is that I will show a bond between oxygen and aluminium. I will show a bond between oxygen and aluminium, and I will put a negative charge here, aluminium tetrahedral species. So please try to understand this mechanism. I could have finished just within the species, like O minus, and then water will come and then alcohol will form. Very simple. But what happens with the other hydrogens? Aluminium is having 4 hydrogens, right? So it's not just single. So this is the species which formed initially, right? Now see, there are 3 other hydrogens are also there, and in the reaction medium you will have lots of carbonyl moiety, right? Now what it will not just stop there. My point is, it will just not stop after addition of one hydrogen. So there are other hydrogens are also there, and then carbonyl molecules are also there. Now see, this hydrogen with its bonding electron pair come attack this carbonyl center again, and it can form again, and this O minus will attack this aluminium. So again there will be an aluminium hydride species. So overall what will happen, an aluminium, again I will have how many hydrogen will be left? 2 hydrogens will be left, right? And then what will happen? O and then CMe2 and then one H is there. So this hydrogen is coming from this lithium aluminum hydride, and then again O and then 2 methyl kind of groups and then hydrogen. Again there will be a negative charge. Now this won't stop there. It will attack further carbonyl group. Then one hydrogen will be left. Then that last hydrogen will also undergo the same process. So overall what happened? We will have a system like aluminium and then O C Me2H, CMe2H, whole 4. This will be formed, and this will end up with getting into transforming Me2CH H here, and this is OH. So this is the overall mechanism, total mechanism. I am not showing just a simple addition of hydride and then OH is formed. So please remember that aluminium hydride is having, and it is so much severe, it will react every other carbonyl system. It's very reactive species. So overall we will end up with this alcohol. So this is a simple case of lithium aluminum hydride mechanism into addition of this carbonyl group. So again, please try to understand the mention that there are 4 hydrogens are there and 4 all of them are reacting. And if you try to get the source, then you can just follow the books in if not all standard books, at least Peter Sykes and other books you will have this mechanism, right? So I will get this structure is clear. And next, what is there? Cannizzaro reaction again. So this is a very simple reaction, and these you have read it in class 12 or maybe in the first time in these also. This is very easy reaction, and I will try to show what happens, and it will cover our 1 hour actually. So let's go here again, our Jamboard, clear the frame. So there are other reactions also, please you can follow. And I had a lot of slides, but I don't think I will be able to cover them all. Anyway, so Cannizzaro reaction, the first criteria we all remember is that this involves hydride transfer. So initially we talked about oxygen, which is the electron source. Then we talked about um, hydrogen as the electron source, and this Cannizzaro reaction is also involve hydride transfer from an aldehyde molecule. So an aldehyde molecule lacking an alpha hydrogen atom. So this is the criteria we always remember, that aldehyde which shouldn't have any alpha hydrogen atom. And there will be question, why not alpha hydrogen atom? What will be the problem with those kind of system, which I am going to say a little bit. So imagine this is your system PHCHO. So it's an aldehyde with no alpha hydrogen. You know, from this with respect to this carbonyl group, this is the alpha carbon, right? Very easy. And now this reaction happen only in presence of very strong base. So 35%, 50% in OH solution and other things. So you have OH minus. So this is an electron source, OH minus. You remember in the first slide itself, I have shown this kind of, ma'am has already shown this electron source, and this is a electron sink is also there. So sorry, I shouldn't have drawn this in this fashion. The arrow should always come from the opposite way. So the arrow, let me change the color. So this O minus can attack here and it forms here. So what we end up with getting? O minus, another hydrogen. It should be tetrahedral. This is just a simple drawing. Uh, so don't worry, it's just not perfect tetrahedral. I am showing it as a pH. So this is what you end up with. Now what happens, this O minus, now it can actually end up here also, like it can form OH, but this again, see, I remember this, it can reverse also. This equivalent to one carbon atom cannot have this two OH group, people will say like that. So it can end up also like this. Now what happens, so there is an important step here. So what happens is O minus is there, hydrogen is there, OH is there. Simple, no problem. Everything is super fine. So we have other molecules also like PHCH, right? And this time what happens? This molecule, this intermediate itself act as the electron source. Again, this O minus. So I will change color to just look cool. O minus will attack here, electron sink, and then it will come there, right? So what happened? Two molecules are getting combined. So I will, so just remember this oxygen is at I made a mistake. So what is the mistake? So it is not the O minus which will attack. So this is not which is the O minus is attacking here. So rather what happens, that's why the first line I remember, this involves, Cannizzaro reaction involves hydride transfer from an aldehyde molecule lacking an alpha hydrogen atom. So hydride transfer from an aldehyde. So I have to remove this, just a second. So that was also a possibility, but like, let's see what happens here. So this O minus will come here. It will form the CO bond. Now it can remove the H minus as a hydride or OH minus. If we remove the OH minus, basically we will end up with the same molecule again. So that is not what happening. So this H with its bonding electron pair will attack here, and this will come here. So this is the case. So here pH, consider this here from here, okay, CH, and then we have OH, and this has become, this hydrogen is transferred to this carbon actually. So this forms O minus, and there is a H, and there is a pH. Overall, just a second. So I shown this hydrogen is getting from this, so there is no bond actually. I showed carbon pentavalent. How is it possible? Sorry. So what we end up with, and so next what happened? So this CH2. So there is another hydrogen. So this green color hydrogen is come up here. Let me change the color. So this is the hydrogen. So this hydrogen is come up here. So overall, we form an acid. See, PHC double bonded OH, and then PHCH2O. This O minus will abstract proton from the solvent. So this becomes PHCH2OH. So these two products are formed. This is a typical Cannizzaro reaction mechanism. Now it doesn't stop here because acid, so it will lose its hydrogen, and will actually what will happen, you will end up with PHCOO minus plus, and then PHCH2 OH. So this is the case, okay, which is just shown here. So overall, this is the mechanism of how an Cannizzaro reaction mechanism happens with an arrow pushing mechanism. And I have covered 1 hour, but I have some other reactions also which I will not describe. You can do it by your own. And this is like electrons, like a radical mechanism, which is shown in shown by ma'am. So how can you get this pinacol magnesium? This is electron involving. Then there is within the same concept acyloin condensation. What will be the product you can do? And also addition elimination reaction is there, and these are very common reactions. If you want to discuss this reaction, I can discuss in the next session, or other will I will try to draw some other things. And carbon nucleophile, so we have shown oxygen nucleophile, hydrogen nucleophile, electron is also there. Then carbon nucleophile can be Grignard reagent, and their mechanism, it's a very different mechanism from the general mechanism you see normally. Then acetylate anions also act as the nucleophile. And carbon anions is like, this is a general mechanism. And aldol reactions, which you are familiar with, I have shown here as a base catalyzed aldol reaction. Overall, this will end up our today's session, and thank you everyone. Thank you so much. So if anyone have any doubt or you want to know anything, please inform me, and I will wait for a few more minutes.
Hello.
Yes, who is this?
Hello, sir. This is Naseem.
Okay, yes, Nasim. Yes.
Sir, can you share the slide?
Okay, I will share. Let me share it right now. Okay, so you can check these things.
Yes, sir. Yes, sir. Sure.
Okay. Can I add here? I don't see attach option. Where can I share with you?
Sir, in the discussion forum
Okay,
in
okay, okay.
NPTEL.
I will share there. Okay, okay, Nasim, I will share there.
Yes, sir.
You will
Yes.
get the slides. No problem. Thank you.
And sir, one
Hmm.
more thing means
Hmm.
when just like you showed an example
Hmm.
where there was a double hydroxy group. So sometimes there are some reactions just like that.
Hmm. Yes.
So we are yes, I am stuck in that means how to do the carry out the mechanism. So can you suggest something so that it will be easier to solve the mechanism?
Uh, can you? Which reaction you are talking about?
Like sometimes there are simple reaction
Hmm.
like you showed that in which there was a double hydroxy group.
Hmm.
The thing I just corrected in that when I said double dehydration, that reaction.
Double dehydration. I didn't discuss actually dehydration. Dehydration. You are saying dehydration. So meaning that water is getting out. Huh. So there is nowhere water is getting out. So I'm getting confused that you were talking about dehydration, but I didn't show any dehydration.
Sir, I was talking about this addition of alcohol in which there was
Okay, okay,
carbonyl.
okay, okay, okay. Got it. Addition of
Yes.
alcohol. Okay. Uh, Someone said, Surya ke, I guess you can attach the drive link of the site. Yes, yes, I will attach. I will attach. Yeah, that's the best thing. I forgot LG actually. Thank you, Surya. Yeah, Nasim, I will come just a second. And Kasi
Yes, yes.
mentioned hydride ions in question. Huh. Hydride ions in question. That is what that O minus was coming back, and this H minus is getting out. And lithium aluminum hydride is also having this hydride. So question of Nasim is that alcohol addition. Just a second, I will show. No problem. So then clear the frame. Let me clear the frame. So I will show you the simple alcohol addition. Okay. So this O, and let just this carbonyl system R O H. Right, Nasim?
Yes, sir.
So it is simple. It will go here and it will go here. Assuming that it's an acid catalyzed, so there will be H plus, and what will you will end up with? There is a methyl group which was there initially, and then hydrogen was also there. This will become OR, and this will become OH. This part is clear to you.
Yes, sir. Yes, sir.
So this is acid, hemiacetal formation. Now, now what is the question? This dehydration. OH will remove that you are talking.
Yes, sir. Yes, sir.
So now it will happen. It will happen in case there is a chance. So this is an equilibria. Okay. So this is an equilibria. So it can go light and left. So now if you have R group has an, it can happen. See, there is H plus is also there, right? So it can what happen is that let's say this OH will become OH2 plus, OH2 plus, and then this methyl. Let me draw as you say, methyl, and then this hydrogen, and then this is OR. So actually what happened, this dehydration, this H2O can get out here. and you will end up with a generating a carbocation. MEH, there is a positive charge here, and OR, and plus H2O. Right, Nasim?
Yes, sir. Yes, sir.
Now, so it will end up getting a carbocation, which is unstable. Unstable in the sense with respect to the reactant, right? So if now you have another within this R group can be anything like CH2, CH2, and then another OH is there. Then only it can forms an stable species. So if your R group don't have, so based on your question, so if your R group don't have this another OH, it cannot be, it doesn't can form this carbocation species and then rest not doing anything. You got my point, Nasim? Hello.
Yes, sir. Yes, sir. I
Uh,
understood.
uh. So let's say if R group is not having anything, not any alcohol. So what will happen actually? It will get back to the corresponding ketone again. So what happened? Let me show you. So this water will again attack overall, and then OH from H2O it will transfer hydrogen here. It will form plus, and it will get revert back. Again it will form ROH. So overall the equilibrium will shift to the left side. So it depends.
Oh, oh.
Sorry.
Yes, sir. Yes, sir. Understood.
Okay, yeah, okay. Thank you. And I can discuss it. If you have any question, feel free me to mail also. I will be there. Actually, one second. I have to stop the recording.